I really like this. Okay. We are going to talk about how derivatives can help us with extrema. Okay. So the first thing I want to talk about is what a relative minimum and a relative maximum are. Okay. This is something that you have talked about in pre-calc last year a little bit, okay, a relative min or a relative maximum. But what I want you to discuss at your pods is how they relate anything to derivatives, all right? So let's maybe draw a picture of a relative minimum or maximum. Can somebody like draw with their finger a curve that would have a relative minimum and maximum? This is what Eric drew. Well, a lot of times over, but okay. This is a relative maximum. This is a relative minimum. It's basically those turning points for a curve. Okay, go ahead and talk about how this relates to derivatives with your peers. All right, so what do you think? How do these relate to derivatives, Trevor?
They have horizontal tangent lines.
Thank you. They have horizontal tangent lines, and how does that relate to derivatives?
You find those by...
What's true about the derivative there?
The derivative equals 0.
Oh. So for our relative minimum and our relative maximum in this picture, our derivative equals 0. Oh. Is there any other kind of graph that would have a relative minimum or maximum where the derivative does not equal 0? Ah. This would be considered, technically it'd be considered an absolute minimum, but for right now we'll just call it relative minimum. What's true about the derivative there? Okay, there, our derivative is undefined. Okay, so I think it would be critical for us to consider where our derivative would be 0 and undefined if we wanted to look into relative minimums or maximums. Do you agree? Okay. So that's something that I need you to write down. Okay? A critical number is where our derivative is 0 or not differentiable. And relative minimums and maximums can only occur at these critical numbers, nowhere else. Now, critical numbers, this is something that we're going to talk about all week. Okay? But I'm just going to slide back for a moment, okay? Where we have undefined derivatives or derivatives that are zero, we have a potential for a relative minimum or maximum. Now, just because it's a critical number doesn't mean you're going to have relative extrema, and we'll talk more about that on Wednesday, I think is when it is. But we have the possibility for them, so we have to consider those places, okay? For sure, if it's a relative extrema, the derivative is zero or undefined, but just because it's a critical number doesn't always mean that, okay? So on the next slide, I'm going to show you a picture, okay? And I want you and your podmates to just talk about which coordinates or which x values do we have relative mins and relative maximums at, okay? Remember, a relative minimum and maximum is basically just a change of direction, like a hill or a valley, okay? So go ahead and look at this picture. Is there a glare from the window? Okay. So go ahead and just discuss, you don't have to draw it unless you really want to, but I want you to discuss the values at which we have relative minimums and maximums. Pod 6, what do you think about relative maximums? B and D are both relative maximums. Okay, and I'm just going to abbreviate if that is okay. All right. Now, D we could consider like, well, no, we couldn't. We don't have like the very highest point ever in the graph because it goes forever in both directions, right? But relatively, it's a high point. And B, relatively, it's a high point. Okay, it's a change in direction. What is true about both of the derivatives at B and D? It equals 0. Awesome. Okay, pod 4, where do we have relative minimums? C and E. What's true about the derivative at E? 0. What's true about the derivative at C? It's undefined. Okay, very good. Now, today I want to focus on absolute extrema, okay? Which means we have to really focus on an interval, okay? So, where's my screen? Okay, there we go. If we have just a minimum, notice how I don't say relative minimum, just a minimum, okay? A minimum is the lowest function value. We call it the absolute minimum. The very lowest value on the graph. A maximum is the very highest function value, right? The highest y coordinate. That is the maximum. Okay, now a graph does not always have to contain a minimum and or a maximum. Okay, and I'm going to show you the different ways that this can happen. Okay. Okay, so I'm going to work with the graph y equals x squared. Does y equals x squared have a maximum? No, because it's going to continue to rise. All right, but does it have a minimum?
Yes.
Okay, our very lowest point is the point 0, 0. So we have a minimum of 0 at x equals 0. Our minimum value is 0, and it occurs at x equals 0. That's how we would describe that. Okay, so now I have y equals x squared, but only from the closed interval from 0 to 2. Do we have a minimum? We have a minimum of 0, right? Do we have a maximum? We have a maximum of 4 when x is 2, all right? So we don't necessarily have two places where the derivative is 0 or undefined, but since we're on an interval, right, a closed interval, we're going to have a high point and we're going to have a low point. Can you tell that that's an open circle? It's a pretty big open circle. Hopefully yours isn't that big, but I wanted to make it obvious. Okay, here we're on the interval open at 2, open at 0, closed at 2. Do we have a minimum? We don't. Okay, we can see that we're approaching that 0, 0, but we can't actually put a value on the very lowest point because we have that open circle at 0, 0. So we would not have a minimum here, but we do have our maximum, right, for at x equals 2. Okay. So if we were to make the entire interval open, would we have any extrema? Not in this case. Okay. Now, that doesn't mean if we have an open interval, we're just not going to have a minimum or maximum. Okay. You know, if we had the open interval from -2 to 2, we would have a minimum. But in that picture right there, we're not going to have a minimum. Okay. Now, one thing we can say for sure, though, if we have a closed interval, and we have a continuous function, so no breaks, then we will for sure have a minimum and a maximum. Okay. Now, before we get into the steps of how we're going to figure out extrema on a closed interval, let me give you a couple of pictures. Okay. So we saw this picture right, and I'm not even. We saw this picture right here, right? Where basically the end points were our highest and lowest point. Right? What about this picture right there? Where would our lowest point be? Like that, what we would look, kind of looks like a vertex, right? But our highest point would be this guy right there, right? This picture, our highest and lowest point would be these two right here, right? Okay, so looking at these pictures, if we are on a closed interval, sometimes we have to look at where the derivative is 0 to get our highest and lowest point. Sometimes we have the very end points, right? If I cut off a graph, I could be cutting it off, and that's the highest point on that piece that I cut off, okay? So if we are looking at a closed interval, we not only have to think about where our derivative is 0 and undefined, but we also have to consider where our endpoints are in relation to the rest of our piece that we have. Okay? So, here are the steps to finding absolute minimums and maximums. Okay? And these are going to be on an interval. Okay, so we're on a closed interval A to B. On the open interval A to B, find critical numbers. Remember, critical numbers are defined to be where our derivative is 0 or undefined. You are going to evaluate your function at each critical number. F of 0 is 5. F of 10 is 22. But then, thinking back to the pictures that we just looked at, we also have to think about the endpoints of our interval. So then you are going to have to evaluate F of at the endpoints to see if your endpoints are higher or lower than any of your critical numbers. And then from that list, the least is the minimum and the greatest is the maximum. Okay, so we're going to go through, let's see, 1, 2, 3 examples. Okay, if you see a problem where you have absolute minimums and maximums on an interval, okay, by the time we get to Friday, like, you should be excited, okay? Because it basically lays out, like, all right, I have endpoints, I have critical points, and I just get to plug numbers and see which one's highest. Like, that's kind of nice, right? Biggest thing we're going to have to be careful with here is the algebra of making our derivative 0. That's something new we need to practice. And make sure you are answering the question that they are asking. Are they asking where the minimum or maximum is? Or are they asking what the minimum or maximum is? Okay? And that'll probably get more into later in the week when we have to be a little bit more careful, but let's just get the basics down. So go ahead and write down this question right here. anytime you see the word extrema, minimum or maximum, the first thing that should pop into your head is find the derivative, okay? Because we have to find critical numbers. What's the derivative of 2x plus 5 over 3? Okay, don't make this too complicated. This is just a linear equation, 2/3 x plus 5/3, right? Which means the derivative is 2/3. Okay. Don't do the quotient rule on this, please, 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 please. Okay, now, we need to look at where the derivative is 0 or undefined. Can 2/3 ever equal 0? Can 2/3 ever be undefined? Okay, so this can't equal 0 or undefined. So we do not have any critical numbers. Okay, so basically we just need to look at what the endpoints are. Okay, we have a line. Which one's the lowest, which one's the highest? Okay. So we need to plug in 0 and 5 into our function. All right? When we plug in 0, what do we get? And when we plug in 5, we get what? 5. Okay. So now we make a decision. This is a pretty easy decision to make, right? We have 2 points. Our lowest one and our highest one. So we have our absolute minimum at the coordinate 0, 5/3, and we have an absolute maximum at the coordinate 5, 5. Well, that wasn't so bad, was it?
It's gonna get harder as it goes on.
Well, yeah, that was kind of just warm up, dip our toes in the water, right? Write this one down. Okay, same process. I see the word extrema, or minimum or maximum. I know I need to find the derivative. Okay? The derivative. 2 minus 2x to the negative 1/3. We just used the power rule, right? Now, last unit, we just got to stop here, right? That probably would have been a pretty exciting one to get on a quiz or test, right? Not too complicated of a derivative. However, we need to determine where this is 0 and undefined, and or undefined. Okay? Now, what you need to keep in mind is that all negative exponents mean that we are really, it's in the denominator, right? So I really need you to rewrite those as positives, okay? Why? Because when we look at where a derivative is undefined, we have to consider its denominator and where that is 0. Okay? Now, in order for us to be able to do that, I think that since one is a fraction and one is not, we need to squish these two together. Okay? So if we create common denominators, we would have 2x to the 1/3 minus 2 all over x to the 1/3. Okay, if I make common denominators. Yes, sir.
Just set it equal to 0 and have it be 2 minus 2 times 1 over x the cube root of x, and then it is the cube root of x equals 1.
Okay, the only thing I don't like about that is you're not looking at where the derivative is undefined. And that is also important. Okay, so we're going to be doing that same algebra drill when we set the numerator equal to 0, but we also need to set the denominator equal to 0 to see where the derivative is undefined. Okay, so if we want to look at where our derivative is undefined, we want that denominator to be 0, right? Cube root of x equals 0 means x equals 0, right? If we cube both sides. Okay. If we want our derivative to be 0, then we would need to set 2x to the 1/3 minus 2 equal to 0. Okay. Now, if we add over the 2 and then divide by 2, we can easily see that x to the 1/3 equals 1. And if the cubed root of x equals 1, then x equals 1. So we have two critical numbers here. X is 0 and x is 1 is, I'm talking about two numbers. They both are critical. Okay. Now, here's something else to think about. Are both of them in our interval? Okay. Could we have critical numbers that aren't in our interval? We could, and then we could ignore them. Okay? So now what we can do is we can make a list of numbers, all right? So we have endpoints at -1 and 3, and we have critical values at 0 and 1. So we need to figure out what the function value is at both of our endpoints. So -1 and 3. And we need to figure out what our function value is at both of our critical numbers. All right, so I'm going to give you a moment to just plug those numbers into what?
The original function.
The original function. Go ahead and take a moment to plug those in, please.
And we need to do 2 as well.
And why would we need to do 2? It is part of the interval, but is it a critical number? Okay, it's not a critical number and it's not an endpoint, so we know it's not a candidate. You could, but it'd just be a waste of time. I think you can do all of them pretty nicely except 3. Is that true?
I was gonna think about
I didn't know that.
one, -1 and 2/3. The cube root of -1 squared, which is the cube root of 1.
But when you have 2 times x, 2 times 1 is 2 times -1. Right. What do we get for f of -1?
-5.
I get -5. What about f of 0? F of 1? And f of 3 is 6 minus 3 radical cubed roots of 9, right? Which is approximately -0.5. 0.240. Okay, so we can make a decision. Our absolute maximum is where? At 0, 0, isn't it? Isn't that kind of awkward? 0, 0? Your maximum. Okay? And our absolute minimum occurs at -1, -5. Okay. Now, I do want to go back and talk about what Joe was trying to say up here. Okay. It's really easy to want to set this right here equal to 0 to get that x is 1, right? But what you have to consider is that this negative exponent means it's in the denominator, and since we can't divide by 0, that can't be 0, right? And so if you were to go ahead and set this equal to 0 right here to get the x is 1, you at least need to consider that we can't divide by 0, and so x can't equal 0. Okay, now I think that for some of us it's a lot easier to see it this way, numerator, denominator, okay? But if you do get you do get going up here and you set equal to 0, at least consider that that is in the denominator and we don't want to divide by 0 for an undefined derivative. Okay. All right, last example. This is where the algebra gets really exciting. Okay, you've all taken a derivative like this before. But it's a matter of setting it equal to 0 that's going to change things. Okay, so I see find extrema on an interval. I know I need where the derivative is 0 and undefined. So, what are we going to have to do to find our derivative?
For product rule.
Product rule, okay? So we have the derivative of the first times, I'm going to write this as x plus 4 to the 1/2. Are you okay with that? Okay. Plus the first times the derivative of the second. Okay. On our Unit 2 test, you left it like that, you got 100, or you got all the points, right? Well, now we actually have to set it equal to 0. Okay? So, we're going to have to simplify this. All right? So, what does this mean? This means we have x plus 4 to the 1/2 plus x over 2 times x plus 4 to the 1/2 power. Do you agree with that? In order to consider where this is 0, since we do have an expression with a denominator, let's go ahead and create a common denominator to add these two together. If you think back to your multiple choice worksheet, we did have one like this where we had to do this algebra. Okay, so this actually is pretty okay. Since this denominator is 2 times x plus 4 to the 1/2, that is what we are going to have to multiply by in order to get our common denominator. And what happens when we take x plus 4 to the 1/2 times x plus 4 to the 1/2?
Equals x plus 4.
It's x plus 4 to the 1. So if we go ahead and we distribute that 2 through, because we can distribute it now that it has to the first power, right? We can't distribute it up here when it has a 1/2 power, but when x plus 4 has a power of 1, we can now distribute that 2. So what we get is 3x plus 8 all over 2 times x plus 4 to the 1/2 power. Or if you want to write it as a square root, that's fine too. Okay? But that's our derivative. Okay. So we need to consider where our derivative is 0 and where it is undefined. So our critical numbers, okay, our derivative is, let's first look at where it's undefined. Where is that denominator equal to 0? Negative 4 would make that denominator 0. Okay. We also need to consider where our derivative is 0. So if we look at that numerator, what makes the numerator 0? Negative 8/3. Okay. But look at this. Is negative 4 in our interval?
No.
It's not. So we really don't have to worry about it because it's not in our interval. But we still have to be able to find it for in the event that it is in our interval. Or we're not working on an interval, like on Wednesday. So now we need to actually test our values. Okay. We have what our endpoints are -3 and 1. And our critical value is at negative 8/3. Okay. So if we plug in these values, if we plug in -3, we get -3 times the square root of 1. Do you agree? Let's go down to 1. If we plug in 1, we get 1 times the square root of 5. I'm going to write it as the square root of 5. And if we plug in negative 8/3, we get negative 8/3 times the square root of 4/3. Okay, that's pretty awkward, but what is it approximately? And I don't know what's wrong with my board. It has like some weird like spot where it's. Okay. So what we have is we have an absolute maximum at the coordinate 1 radical 5, and we have an absolute minimum at the coordinate negative 8/3, negative 8/3 radical 4/3. Okay, or you can put the approximation, that's fine too. Essentially, we have to figure out where the derivative is 0 or undefined for our critical numbers, and then we have to test critical numbers and endpoints, okay? The most strenuous part of your assignment is going to be not finding the derivative, but simplifying the derivative to be able to figure out where it is 0 or undefined. And those are going to be your algebra skills. It has nothing to do with calculus anymore. If you can take the derivative, it has to do with your algebra skills. Okay? Which, here's an opportunity for us to just brush up on those a little bit. Some of you are excited about that, but it's more about the algebra. Some of you may not be. However you feel, doesn't matter. Still got to do it. Okay? And we got to practice it. Okay?